Okay, so we're ready for chapter 8, which you can see as sampling distributions, and it ties in very closely actually with chapter 7, where we talked about the normal distribution. So in other words, in this chapter, everything we do will be based on the normal distribution, but we're going to use the normal distribution in a somewhat different way than what you're used to seeing, because our focus is going to be on samples, okay? Not probability distributions as such, but the behavior of samples. Okay, so anyway, we'll start out by noting that, of course, we know what a sample is. A sample is a subset of the population, and we know that samples are drawn from populations in order to make it easier to estimate the properties of that population. Given that most populations are quite large and that choosing the entire population could be very time consuming, often it is sufficient to choose samples and use their results to explain the properties of a population, assuming, and this is the big assumption, that the samples that we've chosen truly represent the population. If we don't pick our samples wisely, then the results will not be very useful. Okay, so it's a very big area of study, sampling. In fact, if you were actually studying statistics at the graduate level, you could take an entire class or even more where all you do is learn about sampling techniques. Every discipline is different. Every discipline needs a different type of sampling. Here, we're going to use a very simple approach. We're going to assume that all of our samples are what we call simple random samples. And all that means is that each element in this population is equally likely to be chosen. All right. So in other words, imagine that you have a school with 10,000 students in it, and we'd like to pick a random sample of 100. If we assign a number to each student and then randomly pick 100 numbers, then we have a simple random sample because everyone is equally likely to be chosen. There's other approaches you could take, which you might see in disciplines like psychology or biology. We won't concern ourselves with that right now, but here we're going to assume that our samples are chosen as simple random samples. Now, the important detail here is this, though, and this is what the chapter is really all about. Every time we choose a sample from a population and we calculate the sample mean, the chances are pretty good that the sample mean from each sample will be slightly different than from the other samples. It's highly unlikely that multiple samples will have the same mean, although it's not impossible. The probability is quite low. So what that means then is that if we continue to draw samples and calculate sample means, what we're effectively doing is creating a new type of probability distribution with its own unique properties. So that's what this chapter is really all about. But before we get into that, there's a couple of definitions we need to know. The words parameter and statistic. A parameter is nothing but a summary measure of a population, and we've already seen several of them, including the population mean, mu, and the population standard deviation, sigma. Okay, so those are referred to in statistics as parameters. A statistic, on the other hand, is a summary measure of a sample, like X bar or S, the sample standard deviation, X bar, the sample mean. Those are defined as statistics. So all of a sudden, for the first time, it took us until chapter 8 to actually define what we mean by the word statistics. That's kind of interesting. So yes, the word statistic refers to a summary measure of a sample as opposed to a parameter, which refers to the measure of the entire population. So what this means then is that statistics are being used to estimate parameters. So if the samples are drawn repeatedly from the same population, the value of a statistic such as X bar will vary from one sample to the next. So we can treat this X bar as if it were a random variable, because when you think about it, what does a random variable do? It takes the outcomes of an experiment and it assigns them numbers. Suppose that our experiment consists of drawing samples from a population over and over and over again, and each time calculating the sample mean. So the random variable is assigning a number to the sample mean of each sample that we drew from the underlying population. Well, if X bar can be treated as a random variable, that implies that it has its own unique probability distribution. Okay, just like in previous chapters, the random variable here is going to have its own probability distribution. Now, because we are defining our probability distribution on a sample statistic, instead of calling it a probability distribution, we give it its own special name, which is a sampling distribution. So when you see the words sampling distribution, remember, it is actually a probability distribution, but a very special one. It is a probability distribution that refers to the properties of a sample statistic. Okay, now in this chapter, we'll be focusing on X bar, but there's others we could use as well. Now, here's an example. I put this together. Imagine that we are doing some kind of marketing research, and we're picking groups of 5 people from some population, and we're using the 5 numbers that we draw. Actually, what we're drawing here is people's ages. So in other words, we find 5 people, we ask them what their ages are, we write them down. So we have 5 elements, X1 through 5, in each of our samples. And for each of our samples, we then can calculate the sample mean, which gives us a single value of X bar. Okay, so now, of course, these numbers are completely made up, but you can see what's happening here. In the first sample, the ages of the people were 4, 55, 19, 54, and 44. That works out to an average of 35.2. The second sample was a little bit older, and in fact, there's somebody in there who's 97. Wow. And so their average is 55. And you can see, if I do this enough times, each of these X bars can be used to describe a sampling distribution. And what that means is that these X bars will have their own mean and their own standard deviation, not to mention a probability distribution. Now, if you were to draw this with a histogram, this is what it would look like. And you can see those bars are sort of randomly scattered around. There doesn't seem to be any particular pattern. This doesn't fall into any of the categories we've already seen. In other words, this is not the binomial distribution. This is not the Poisson, although because we only have a handful of samples, it appears to be a discrete distribution. But if you notice on the horizontal axis, we have categories, ranges of ages, 10 at a time, 0 to 10, 10 to 20, 20 to 30, up to 100. Now, here's where it gets interesting. What if I did the same thing, not with 5 people at a time, but 20? Okay, in other words, instead of walking around and randomly picking 5 people at a time and calculating the sample mean, I'm doing this with 20. So logically, when you think about it, with such a small group as 5 people, the chances of the means being very different from each other is actually pretty high. I mean, imagine yourself just randomly walking around, let's say, the Westchester Mall, and you randomly pick 5 people at a time. The sample means could be anything from teens up to, let's say the 90s, or any age that you can imagine. But the larger the groups are, the less likely the sample means are to be either very large or very small. Okay, so even if you have a group with children in it, if there's 20 people in there, the chances are there'll be some adults as well. So the average age is not going to be extremely small, or it's not likely. And the same thing on the upper side, unless you inadvertently pick 20 senior citizens in your sample, the average age in that group is not going to be as different from one sample to the next as it would have been with 5. So in principle, as I keep increasing the sample size, the sample means themselves will be much, much closer to each other. So what I did here was I drew a new histogram for 20. And all of a sudden you can see what's starting to happen is the means are much more clustered around the center than we had back here, where they were quite a bit spread out. Okay, so if I increased it even further, I would end up having just a couple of very tall bars in the center. Now, what's interesting about all this is that what this is implying is that the variances and standard deviations of the large samples will be smaller than for the small samples. Okay, in other words, if I were to calculate not just the means, but the standard deviations, you can see that the standard deviation would be larger within a group of smaller samples because the means are so spread out. Anyway, so what are we building up to here? It turns out that based on an incredibly important result in statistics, which is called the central limit theorem, the behavior of these X bars is approximately normal. Okay, so in other words, we can justify using the normal distribution to calculate probabilities for sample means. So under what conditions can we do this? Well, the central limit theorem tells us that there's two conditions under which our sample means can be treated as being normally distributed. Number one, if the samples are chosen from a population which is itself normal, then the means themselves have to be normal. In other words, the means of a normal population will themselves be will be normal. So if you're sampling from a normal distribution or some normal population, then the sample means that you generate will follow the normal distribution. But even if that's not so, or if we're not sure, if the sample sizes are at least 30, then we don't have to worry about whether the underlying population is normal. It means that the X bars themselves are going to be at least approximately normal, close enough that we can use the normal distribution. So what does that leave? What case does that leave? Well, when we have non-normal populations and small samples, that case isn't covered here. And for those, you cannot use the normal distribution. So we're going to see what we have to do instead in a later chapter. Okay, but for now, it's enough to note that the sample means are going to be normal if the underlying population itself is normal, or if the sample sizes are at least 30. That's all it takes. So we're going to assume in the rest of this chapter that we do meet these requirements, and then we're going to do some calculations. Okay, so the X bars will then be normally distributed. They will follow the normal distribution, and they will have their own unique set of moments. Okay, in other words, we will have formulas for calculating the expected value, the variance, and the standard deviation of X bar. Now, I tried to illustrate, I hope these graphs kind of make sense to you. If you look in the upper left-hand corner, I've got this wacky distribution for X. X could be, this could be any distribution you can imagine, but certainly it's not normal. What this is trying to show you is that if I draw samples of at least 30 and create a distribution of X bars on the right there, you notice how that curve is normal, okay? Because we chose samples of at least 30. So even though we picked them from a non-normal population, those X bars on the right are all normally distributed. Okay, that's all it took. Now, on the bottom, the X's are already normal to start with. So the sampling distribution of X bar has to be normal too. By the way, there's some notation here that we need to introduce. You can see it down there, but I want to make it bigger because it's a little small there. You're used to seeing certain types of symbols being used here for moments. You might recall, for example, mu, which is the mean. Now, we often use this for populations, but we also use this for a probability distribution. Although when we do, we often write it as expected value of X. Okay, so there's expected value of X and mu mean the same thing. In this context, they both represent the mean of a probability distribution to distinguish it from the mean of a population. Now, you might wonder, why don't we have different notation for these different cases? Well, we don't, but it should be clear from whatever problem you're working on that you are in fact treating this as the mean of a probability distribution. In other words, the mere fact that you're being given samples means you're clearly not calculating the mean of a population. The variance, oh, and by the way, when we're dealing with the sampling distribution of X bar, we have to make this a little different. Ooh, we're going to introduce the notation mu X bar is the mean of the sampling distribution, specifically the sampling distribution of X bar. So only in the case when we're dealing with X bars, if we're creating a probability distribution by repeatedly sampling, the resulting X's will have their own mean, which we will write mu X bar. And by the way, in this case, you can also write this as expected X bar because it's the same thing. Well, then, what about the variance? What should we do about that? Okay, so clearly this is the variance of a probability distribution, like the normal, which we saw in the last chapter. I'll just abbreviate that, dist. If we're specifically dealing with the sampling distribution of X bar, we're going to put that little subscript there so we can tell them apart. And of course, I'm sure you can see what's coming next, the standard deviations. Standard deviation of a probability distribution, and then this would be the standard deviation specifically of the sampling distribution of X bar. Now, if we were trying to create a distribution for a different sample statistic, like let's say S, the sample standard deviation, then the subscript would become an S. Okay, it would just change to whatever case we're looking at. Now, here's something you got to watch out for, though. And this happens in statistics fairly regularly. We often have multiple names that mean the same thing. So let's add this little detail here. Note, for a sampling distribution, the standard deviation is often referred to as the standard error. Now, don't ask me why. That's just the way it is. The words standard error referred to the standard deviation of a sampling distribution. Although the standard error is a standard deviation, it's a special type of standard deviation. So just to make sure that it's crystal clear that we're dealing with a probability, a sampling distribution, sometimes the terms can be a little bit different. Okay, so just be aware that the words standard error means specifically the standard deviation of some sampling distribution, not just X bar. This will show up again in stats decision making, by the way. So something to look forward to. You'll be seeing more sampling distributions as you go forward. So we have our moments then. What we want to know is how to calculate them. Okay, so it turns out that we have specific formulas for calculating the moments of the sampling distribution of X bar. They're not that complicated, but we have to understand how they work. Okay, and here there's a reminder. The little subscripts are there to help us remember that this is specifically about the distribution of X bar. rather than the underlying population. Okay, now, how do we figure these out? Well, they both have the same mean. In other words, the x's themselves and the x bars have the same mean. In other words, if I am drawing, let's say I'm drawing samples of ages for Americans. What if it turns out the average age for all Americans is 29? If I continue to draw samples, the average of all the sample means will also be 29. Okay, now if I only draw a few very small samples, not necessarily, but in general, if I sample enough and the sample sizes are large enough, the population mean and the mean of the sampling distribution will be the same. And in this case, 29. All right, so that one is easy. The next ones are not so easy, okay, because the sampling distribution of X bar will tend to have a smaller variance and standard deviation than the X's themselves. For the first time, we need to compare the sample size with the underlying population. And by the way, we mentioned earlier in the course that we make a distinction between the sample size, lowercase n, and the population size, capital N, because sometimes both of these occur in the same formula. Well, now we're going to see that. So for the first time, they will both appear together. And what we're going to try to do is show that the ratio of these two is what determines what to do about the moments of X bar. Okay, not the mean, but the standard deviation and the variance. So here we're going to think of small and large in terms of what proportion is of the population is in each sample. Okay, so if the samples are huge, then we have a large sample. If they're small, we have a small sample. And the cutoff point between large and small is 5%. Okay, so what I've done here is I've summarized these for you. If we have a small sample, then these are the formulas you will use for the variance and the standard deviation of X bar. What you're doing is you're taking, in the first case, the population variance and you're dividing it by the sample size. In the second case, you're taking the square root of the variance of X bar. Now, what about the large sample case? Well, with the large sample case, that reduces the variance of X bar from one sample to the next. So we have to adjust these formulas to reduce them a little bit, not a huge amount, but enough to make it important. And so this is what the results look like with a large sample. And so for the variance, we have this term n minus n over n minus 1. And for the standard deviation or standard error, we have the square root of that same term. And unless the difference between capital N and lowercase n is huge, this number will be slightly less than 1. We're just trying to knock the variance and standard deviation a little bit down to reflect the fact that we have a large sample, which means that the means should be more similar to each other than for small samples. By the way, this term, not the one on top, the square root, this one has a name in statistics. It's called the finite population correction factor. Okay. It's meant to tell us what to do, how to adjust when we have larger samples. Now we're ready. Now remember, according to the central limit theorem, we can treat X bar as normal under certain conditions. We'll assume that those are being met here. We have an underlying normal population, or else we have large samples. Now, You don't be confused about large and small. The central limit theorem bases large and small just on the sample size. For what we're doing here, the moments are based on the sample size versus the population size. So assuming that the conditions of the central limit theorem are met, X bar is normal. And if you want to calculate the probabilities for X bar using the tables, instead of the traditional formula, Z equals X minus mu over sigma, we replace that with X bar minus mu X bar all over sigma X bar. That number, whatever it is a standard normal random variable, Z, which can be looked up in the tables. And this number, by the way, is known as a Z-score. The alternative is to whip out the old calculators and just use normal CDF like we've done in the past with the mean of mu X bar and the standard deviation of sigma X bar. So we can do it both ways very quickly and easily. And of course, you'll recall that standard normal means the mean is 0 and the standard deviation is 1. All right, actually, you know what? I forgot to open up the tables. Let me just do that real fast. And of course, it's up to you if you want to use the tables or the calculators. All right, we have the positive and the negative. Okay, we need them both. Oops. There we go. Nope, that's not it. I was trying to reduce the size of this a little bit. There we go. There we go. Okay, so here's a simple example. A hedge fund holds a portfolio of 10,000 stocks. That's our population, by the way, and capital N is 10,000. We know from historical experience that the population mean, by which we mean the mean of all of these stocks, this is our population, is 10% per year, and the standard deviation is 20% per year. So if you could visualize grabbing a sample of 100 of these stocks, we can now use these techniques we've been studying to calculate probabilities for the mean of that sample. Okay, so let's do some calculations here. So first things first, and you can see what are we being asked to calculate. First, the probability that X bar is greater than or equal to 8%. Secondly, that it's less than or equal to 12%. And finally, somewhere between 7 and 13%. Okay. Now, the first thing we always have to do is determine if we have a large or small sample. Okay. The cutoff is 5%. But if you can see, if you took the ratio of lowercase to uppercase n, that's 1%. Okay, the sample is only 1% of the population, which means we have a small sample. And that means that we can come back here and remind ourselves that, number one, the mean of the samples is going to match the mean of the population. Okay, so that's the easy one. What about the variance and standard deviation? That means we're using these two cases. Small sample. All right, so let's do that. So the mean, the population mean, and the mean of the sampling distribution are both 10%. And since we have a small sample, the standard error, by the way, when you're using the calculator, you don't really need the variance. It's that standard deviation of X bar or standard error that we're really interested in. So we're taking the population standard deviation of 20%, divide by the sample, square root of the sample size of 100. That means sigma X bar is actually 2%. So whether you create a Z-score or use your calculator, that is what you're going to use, 10% and 2%. So for example, in the first case, remember we were asked to calculate the probability that X bar is greater than or equal to 8%. So I'm going to use my transformation formula so I can use the tables. I'm subtracting 0.10, 10%, and divided by 2%, which we just calculated. So here, X bar being greater than or equal to 8% is equivalent to having a z-score of greater than or equal to -1. Now, of course, as you recall, the tables don't have greater than or equal to probabilities. So I'm going to rewrite this algebraically as 1 minus the probability that z is less than or equal to -1. Now that we can find in the table. -1 would be at the intersection of -1 and 0, 0. 0.1587. Okay. But remember, we have to subtract that from 1. So the actual probability is 0.8413. So if you look at these two graphs that I've created, the top one is for X bar, the bottom one is for Z, the standard normal distribution. It shows us that what we just proved is that X bar being 8% or above is equivalent to having a z-score of -1 or above, which in turn is equal to 84.13%. That's all there is to it, huh? Yes. Now, if you decide not to use the tables, this is our old friend normal CDF from the last chapter. The only thing you have to watch out for here is that the calculator says mu and sigma, but for this particular application, remember, you're actually doing mu x bar and sigma x bar, right? But other than that, nothing has changed. You're still calculating a normal probability. And here I've got 8% for the lower limit, positive infinity for the upper limit. The mean of X bar is 10%. The standard deviation or standard error is 2%. And I get the same probability that I did with the table, which is 8413 or 0.8413. So you can see it's not very difficult. Really, all you have to do is figure out the values of mu x bar and sigma x bar, and you're all set. Then you can do whatever technique you want. Now, the next one was less than or equal to 12%. So if you convert that to a z-score, you can see that this is equivalent to z being less than or equal to 1. And on our table, we just got through showing that, well, actually, no, we didn't. That was the other one. 1.0 is right here. Oh, yeah, 8413. Okay. By the way, you know what, I did this on purpose so you can see why this is the same as the previous case, because on the right-hand side, you're looking at a z-score of 1 down to -infinity. On the left, it's -1 up to positive infinity. Due to the symmetry of the normal distribution, these have to be the same. Okay, and remember symmetry. There's a balance between the left-hand side of the mean and the right-hand side. For the calculator, we're looking at 12% up, down to -infinity. So the lower limit is -infinity or -2, 99. The upper limit is 12%. These two are the same. Remember, these refer to X bar. This is the mean of X bar. This is the standard deviation of X bar. And once again, we have 84.13%. Okay. Now for C, again, we do not have in-between probabilities in the tables. Using our conversion formula, subtracting 10% divided by 0.02 means we're looking for the probability that Z, the standard normal random variable, is between plus and minus 1.5, which means we have to subtract. So 1.5 is right here. 93, 94. Oh, okay. This is, oh no, what did I do? I got the wrong one. Sorry. 93, 32. That's better. Yeah, much better. Okay, it's because it's 1.50. That's why it's this cell right here. 1.5 combined with 0.0. Now we do the same thing on the negative table. Negative 1.50, 0.0668. The difference between the two is 0.8664. You can see the diagram up here tells us that we're looking for the probability of being within 1.5 standard deviations of the mean. Turning to the calculator, what's different now is that we have lower limit of 7%, upper limit is 13%, and we still end up with 0.8664. All right, now let's look at another example. This will be an interesting one because now all of a sudden, for the first time, we have a large sample. We have a collector with 120 paintings in this portfolio, so that will be our population. The average price is $1 million, and the standard deviation is 120,000. We're going to choose a sample of 10 of these paintings. So lowercase n is 10, uppercase is 120. That is a ratio of about 6%. No, 8%, sorry, 8.3%, which means that for the first time, we have a large sample. What will that affect? Let's go back and look at our calculations from earlier. And we'll remind ourselves that that means these are the calculations we'll use for the variance of X bar and the standard deviation. Okay, we need these extra terms here when it's a large sample. So you only have to do those once. Once they're done, you can do as many calculations as you want. So for example, we're looking for the probability that the sample mean is greater than 1 million, less than 950, between 975 and 1025. Now, this first one is almost a trick question, okay? Because whenever you are asked to calculate the probability that a normal random variable is above the mean, no matter what the mean is, the probability of being greater than that mean is a half. So you really don't have to do any calculations here, but if you forgot that, what you do is go ahead and you first recognize that we have a large sample here because 10 is about 8.33% of 120, which means we need the formulas that I showed you a minute ago with the extra terms to reflect the fact that this is a large sample and that the variance and standard deviation will be reduced as a result. Okay, so we need these two formulas for what's about to happen. We don't have to worry about the mean. We know that the mean of X bar is the same as the population mean. That's easy. So the mean is $1 million, fine. It's the standard error or standard deviation where we have all these numbers. We need the so-called finite population correction factor. And so if you plug in these numbers, and now because we're dealing with dollar amounts, we're going to round this to dollars and cents. The standard deviation or standard error is approximately $36,484.14. It's not exact, but it's close enough. Now we're going to go ahead and do our normal calculations. We're going to either use our transformation formula to convert these into z-scores and then use the tables the normal way, or else we'll use our calculators. So for this one, like I said, it should come as no surprise to you that because 1 million is the mean of this distribution, this probability of being greater than or equal to the mean is just a half. But if you go through the formality of doing this transformation, you'll see that what we're asking for is the probability that z is at least 0, or equivalently, 1 minus the probability that z is less than or equal to 0, or 1 minus a half, which leaves us with a half. Any way you slice it, the probability is a half. On the calculator, we're looking for $1 million up to infinity for lower and upper limits. The mean we determined is $1 million. Standard deviation or error is 36,044.14. Now, you may have run into this before with this calculator. One of the quirky things about it is that for this case, greater than or equal to the mean or less than or equal to, it doesn't exactly get it right. You notice how it's got 0.4999999. It should be exactly a half. Why is this happening? Because this second comma 99 is not exactly infinity. That causes a trivial rounding error, but just be aware, this is actually a half. Okay. You want to run into this once in a while. You run into these very trivial rounding situations because we don't have a true infinity for this calculator. Now for B, they're asking for the probability that the mean is less than or equal to 950,000, which turns out to be the equivalent that z is less than or equal to negative 1.37, which we can easily find in our table. Where would that be? Negative 1.37. Here we go. 0.0853. Okay, and that's it. We're done. For this one, that's all we had to do. No more rearranging. We're done. Okay. On the calculator, keeping in mind these two stay the same. This time we're looking for 950 down to negative infinity. And that's also going to give us 0.0853. Now, you may ask yourself, well, dollars can't go below 0. Why don't we just put a 0 here? You could. But the difference would be so minimal that you'd never notice it. Okay. Because what you're really looking at here is standard deviations below the mean, which can be negative. So you don't have to worry about the 0. I mean, technically, yes, you could put a 0 there, but it's not necessary. It won't really improve the accuracy at all. And then finally, we have an in-betweener, 975,000 up to 1,025,000. As usual, we can convert this into z-scores, which in this case happens to be between negative 0.69 and positive 0.69. So we have to subtract one from the other, which we've seen many times before. Go to the two tables. We have to look this up. Once in the positive table, 0.69 is right about here. Okay, at the intersection of 0.6 and 0.09, we find 0.7549 right there. And on the negative table, negative 0.6 combined with 9, 0.2451. The difference between the two is 0.5098. And if we throw this into our calculator, you can see the range is between 975 and 1025. And there could be, 5098, 5068. That's rounding. Okay. There often can be rounding differences between the tables and the calculator. Okay, now here's something interesting. Up to this point, our entire discussion has revolved around the sampling distribution of X bar, the sample mean. It turns out that we can do the same thing with the sampling distribution of the sample proportion. Okay, we haven't really done a lot with the proportion up to this point. The proportion means, for example, if I ask what proportion of people are left-handed, what I really mean is what percentage of the population is left-handed? 8%, for example. And what's good about this proportion is that it actually follows the binomial distribution. But we already know that as the number of trials increases, the binomial distribution gets progressively closer to the normal distribution. So that means that to calculate probabilities for the sample proportion, you can also use the normal distribution. It's the central limit theorem doesn't need to be invoked here because we know that proportions follow the binomial distribution. Which, by the way, why is that? Because if you think about it, if I'm thinking about the proportion of lefties, well, realistically, the population, everyone's either a lefty or a righty. Okay. Let's pretend that there's no ambidextrous people, lefties, righties. So you can see that that is a binomial situation. And that means that in the limit, that goes to becomes normal. So let's say that we want to know the proportion of voters who can't favor a specific candidate. Now, every time there's an election, you see all this information on TV. They don't often mention to you that there's no way that they contacted every voter to find out what they thought about an issue or a candidate. They use samples. Sometimes in the bottom of the screen, they'll mention the sample size, but it's very rare. What they'll do instead is they'll give you a number that indicates how much uncertainty there is associated with their results. Like it might say plus and minus 2%, which means that based on the fact that this is a sampling distribution, suppose that they told you that the proportion of people who favor a certain bill to be passed is 40%. And then in the tiniest imaginable print, it says plus or minus 2%. What they really mean is that their best guess is 40%, but it could be as low as 38 and as high as 42. Because again, there's uncertainty associated with choosing samples rather than the entire population. Okay. Well, now we're going to define the sample proportion P as X over N, where X is the number of successes in a series of N trials. All right. So if, for example, you were told that in a class of 46 students, 4 of them are left-handed, 4 of 46 is 0.087, that is our sample proportion of lefties. By the way, because we're using lowercase p for the sample proportion, we're going to use capital pi for the population proportion, okay? Because pi is the Greek equivalent of p anyway. So if we're using p for sample proportions, we're going to then turn around and use pi for population proportions. And remember, I did mention when we were looking at the normal approximation of the binomial that this would come in handy down the road. Now it's coming in handy because this is what we're doing here. We are actually not going to use the binomial distribution at all. We're going to use the normal approximation to the binomial. Okay. And we've already seen that this should work reasonably well as long as n times pi is at least 5 and n times 1 minus pi is at least 5. Okay, so what are the moments then for the sampling distribution of P? Well, the mean or expected value P is equal to the population proportion pi. Okay. Oh yeah, it says it up here. Pi is meant to be the population proportion. And all that means is that on average, if I keep drawing samples, the proportion of lefties will be the same as it is for the entire population. Now, the variance and standard deviation are actually taken from the binomial distribution. Okay. So here's our variance and here's our standard deviation. But now here's where we have to watch it. Even here, we have to know if this proportion, the sample is large or small compared to the population. So these are the two cases for small samples, And with large samples, we still need our old friend, the finite population correction factor. So once again, for large samples, we do need to make a correction, right? because otherwise our results will not be accurate. It's just that simple. In statistics, a lot of results that we use are for practical reasons. It works. Okay, it helps explain the real world. Whereas in other branches of math, like calculus, you can't get away with that. Everything you do has to be proven. It's not good enough to say, well, this seems to work. That doesn't fly in calculus, but here, yes, we can do that. All right, so there's a little chart for you so you can remember. Here's an interesting one. The US government data show that 15% of Americans are retired. That's our population proportion. The government wants to know if the proportion of retirees in New York State is 20% or more. So they pick a sample of 200 New York residents. What's the probability that, given that the population proportion is 15%, the probability that in this sample, the proportion is 20% or more? So we need to calculate our moments. Okay, this is just equal to the population proportion of 15. And since this is this is a very small sample. How do you know that? Well, I mean, it doesn't say here, but the population in New York State is many, many millions of people. How many? I'm not sure, 20 plus million, let's say. But clearly 200 is a very tiny percentage of 20 million. So we're going to treat this as a small sample. So these are the two formulas that we'll need. I guess I looked it up. I'd forgotten. 19.45 million. Okay, I said 20. All right, that's fine. And so we have our variance and we have our standard deviation. So now we can calculate any probabilities that we want. And what we specifically were after. Oh, by the way, if you're going to use the tables, to get your z-score, this is now what you have to do. P is the sample proportion, pi is the population proportion, n is the sample size. So if you want to use the tables, this is what you have to do. So remember, we were after the probability that the proportion of retirees in New York State is at least 20%, which is equivalent to z being greater than or equal to 1.98, which means we have to subtract that from 1. And if you go to your table, the positive table, for looking for 198, we have, where is it? 1.9 combined with 0.08 is here, 9761. And so when we subtract 1 from that, from 1, we get 0.0239. Okay, so in other words, it's not likely that the proportion of retirees is that high in New York, given that the national average is 15%. Okay, so let's say that for some reason the government was going to send more money to New York State if that was true, but it doesn't look like it's very likely. And of course, in the calculator, we calculated the mean. We just did that, remember? The mean was, oh, where did it go? Oh, there it is, 15%, 0.15. The standard deviation or standard error is 0.02525. Those are the moments we'll use. The probability that we're aiming for is 0.20 up to infinity. And again, technically this can only go up to 1, but it'll make no difference at all if you write it as infinity, because this is the normal distribution. And it's about 0.02384, about 2.4%. Almost exactly the same as what we had here. Not exactly, but very, very close. So that is our discussion about sampling distributions. We now know how to calculate probabilities for X bar, the sample mean, and P, the sample proportion. The key to the whole thing is knowing how to calculate the moments and then either going to the normal table with z-scores or using the calculators with our old friend normal CDF. Okay. What's coming next? Now, chapter 9 is our introduction to what are called confidence intervals, which is kind of an important idea. And we'll be learning in that chapter a brand new probability distribution, which will be critically important in stats decision making. Luckily, although the calculations can be messy, the calculators can help us a lot with what we're going to do in chapter 9. And that, by the way, is the last chapter of the course. So we're in pretty good shape. We're not running out of time or anything. And so the chapter 8 and 9 will be the content of the final exam. Okay, the final exam will not be comprehensive. It'll be just in these last two, 8 and 9. Okay. So anyway, here's our discussion of chapter 8. So we can go back and practice some more problems, but we're basically done with this. All that remains, like I said, is confidence intervals. Now, when you get into stats decision making, you'll be starting with chapter 10 most likely, which is the introduction to hypothesis testing. Some stats decision making courses actually step back a couple of chapters and review them, I've discovered. And some of them, like mine, will just start at 10 and take it from there. So, but 10 is the sort of the link between stats 1 and stats decision making. It's assumed that everybody got through chapter 9, confidence intervals, when you start stats decision making. All right, I think that's a very comfortable assumption. So because it's almost August, by the time September rolls around and you're sitting in that class, you should be really sharp and on top of this material. It'll be fresh in your memory where everyone else hasn't thought about it since April, really. And yeah, it's kind of nice that you'll have all of this information freshly stored in your memories. And so, because let's face it, it's a long summer. It's easy to forget what you learned in the spring. That won't be a problem for this group, that's for sure. All right, so I will see you then next time, and we'll be looking at our discussion about confidence intervals. All right, so good night, everyone.